I'm Lukas Taegert from Rollup.js, and today I want to talk about how we are reinventing Rollup. Now, this may sound big, but before I get there, I would like to take a look back. So what happened in the last year? What were the new developments for Rollup.js? And for the features I want to present to you, I prepared a series of examples. So at the bottom of the conference window, you should be able to find a tab where you can actually look at the examples and play around to see how the features actually work. Just let me go quickly over some of them. So the first does not have an example, but the code splitting algorithm got much faster for large projects. We had a report from a user that Rollup was taking basically 2 hours for their project to build, and they did some digging and they found out that most of Rollup was okay fast with about 5 minutes, but it took 2 hours for the code splitting algorithm to complete. Now we seriously started tweaking that algorithm, replacing set operations with big integer operations and so on, and we managed basically to get the code splitting time down from those 2 hours to a few seconds. So this may be a big step, and if you have a large project, this should be a huge win. Next, we have treeshaking now for dynamic imports. This was an external contribution from Anthony Fu. Very big thanks for him. Basically, it means if you use destructuring patterns when using a dynamic import, either with async await or with a promise syntax, then Rollup will detect this and only include the imports that you actually use. Next, we have the no side effects annotation. So you may know that there is a pure annotation that you can place in front of call expressions. No side effects annotation is an annotation you place in front of a function declaration, which makes it much easier because you may be calling the function 20 times. Now you only need this annotation once in front of the declaration, which is also a nice feature for libraries, as long as the final bundler that is used also supports this annotation. But I think at least ESBuild is going to support it, and maybe others as well. The next feature is experimental, but I still want to talk about this because it basically took months that I worked on this and sparked other features. So at the end of my last ViteConf talk last year, I mentioned that I wanted to do something about reducing the number of chunks based on a chunk size limit. And the problem is this. So for now, the paradigm of code splitting in Rollup has been that we never want to duplicate code. So there is no dead code as far as we can do in the final created bundle. But that means if you want to reduce the number of chunks, you have to load chunks earlier than when you need them. And since Rollup does not wrap your code in function closures, we can only load code earlier if it does not have side effects. So for instance, you could load a function declaration as early as you want because nothing will happen except a variable will be created. But you cannot load like a log statement or something because that will be a side effect that happens earlier. So obviously a lot of work went into this, and I think the result is still not 100% satisfactory. And it heavily relies, as I said, on detecting side effects. But this also motivated 2 other features. The first is experimental log side effects. So we have logging for side effects to find out what Rollup actually thinks is a side effect, because it may not be what you think is a side effect. For instance, calling a global function may be a side effect, or accessing a property that may not exist, or doing something with a variable that has been reassigned. So what experimental log side effects does is it logs the first side effect it finds in each module to tell you basically what the first effect is, and so that you can gradually remove side effects as you go. And if you don't know how to remove them, there is now also this one, manual pure function, which allows you to basically eliminate side effects from functions, or basically declare functions as pure via configuration just by name. To say basically every function named foo does not have side effects. So this is great if there are side effects in your dependencies where you cannot just edit the code. So these were features for end users. There are also features for plugin authors. And again, I prepared a series of examples for those that you should be able to find at the bottom of the window. The first thing is tree shaking for emitted assets. So imagine your code is referencing, I don't know, a worker or a file that is to be loaded from disk, and the code referencing it is not included. Previously, emitting a file meant the file was part of the bundle, but now you can add an additional flag needs code reference. And if this flag is added, then an emitted file is only really added to the bundle if there's at least one import.meta.file URL reference in the code that is not removed, which I think is a useful feature for many different usages. Then next, also about emitting files, there's a new type. So previously you have chunk and asset. Now there's a third type, pre-built chunk. So a pre-built chunk is basically a mix-up between an asset and a chunk. So the limitation of chunks is that you can only emit chunks during the build phase, so the first phase while the module graph is being generated. But some people want to add chunks at a later stage when the output is generated. Pre-built chunk means you're basically emitting an asset where you supply the entire source code, but you're also adding some metadata, saying this has the following exports, for instance, or the following source map, and then Rollup creates a chunk that has the metadata of a proper chunk, but just contains the code that you have. And you can add this at any time, and other build tools will pick this up as a chunk, and you need to reference it as an external import from other files. Just have a look at the example to see how this is meant to work. Another tool helpful for debugging is the new resolved by field. So you can use this resolve to figure out how Rollup would resolve an import. And the new field tells us which plugin actually resolved the import to debug if your resolver is actually kicking in, or maybe some other plugin is catching the resolution for you, which could also mean that the plugin order is wrong, or maybe it's an internal Vite plugin that is messing up your resolution. So this could be really helpful. And lastly, there is a new logging API, which is really big. So you may know that there is this.warn to emit a warning from a plugin. Now you have two other functions, this.info and this.debug. The difference is that debug is hidden by default and info is shown by default. And you have a new log level option to control which levels are shown. But there is more. So info and debug not only accept strings, they also accept complex objects. So you can add any metadata to infos and debug messages, just as you could add any metadata to warnings. And plugins can also define an on log hook to react to logs of any level and augment logs with additional information, replace logs and filter logs, or just, I don't know, write down the logs in some way. So I think this is also a really useful feature. I'm not sure how much Vite did pick this up. I hope this is kind of merged into the Vite logging API. So, but the thing is, okay, these were a few solid improvements, not as many as I would have hoped to be there in a year. But the thing is, there was two major complaints that I didn't address. This is bundling speed and memory consumption. And the problem is Rollup is already pretty optimized with regard to bundling speed, and reducing the memory consumption would also mean thorough refactorings of Rollup. And the thing is, to achieve this, maybe we need a different technology. So this gets me to my second part, replacing the engine while driving, which I said we are reinventing Rollup, maybe not as a whole, but piece by piece. So let's do a profile of the bundling speed. So this is an example build. It's just one single file. It happens to be the browser build of Rollup that I used as input. So it took on my machine about 800 milliseconds to build and 80 milliseconds to render in the end. And from the build time, the biggest chunk was generating the module graph. So what does that mean? Basically, first it's reading the files and it's turning the strings into object structures, which is called an abstract syntax tree, which later steps then can use to derive what imports are there, what function declarations, and so on. So this is done by an external tool, which is called Acorn, and which takes, in my example, 180 milliseconds. And there's another step, analyze syntax tree, where we now then translate these structures into Rollup internal structures and do some analysis, do scope analysis, and so on. And there's another big step is tree shaking. But my goal was to start with the syntax tree, replacing that step as a first step. And then when we have this maybe as native code, we could start growing this and start converting some of the later steps to native code. But as a very first start, maybe we go with just replacing the parser with something that's out there, the speedy web compiler. So SWC is really fast, maybe not as fast as ES-Build, but very close. And the advantage is that it's written in Rust. Rust has very nice community support, great JavaScript bindings. So if I want to write native code, Rust may be a good choice. So what happens? I'm using the JavaScript bindings of SWC core, and just passing the same code. And it took 270 milliseconds, which is compared to 180 milliseconds for Acorn. What happened here? This is slower. Okay, so let's get back. How about using SWC from Rust? And now we see when I'm running SWC from Rust, it takes 51 milliseconds, which is really good. So this is where we want to go. This is 3 times as fast as Acorn. So where did the remainder of the time go? Obviously, it's somewhere in between native code and JavaScript code. It's JSON serialization. So SWC, in the end, is creating a string JSON representation of the syntax tree. Then this is copied over into JavaScript, and then JavaScript objects are created from that string. And this is the costly part. This takes 220 milliseconds. And there were more issues. The syntax tree created by SWC is very non-standard. You can see there is a standard for syntax trees. It's called ES3. It originated from Mozilla and has been maintained for years by a group of volunteers, which involved Babel and eslint and other tools. But SWC just made their own, which makes it hard to use by Rollup. And also the positions encoded in the syntax tree, so the string positions are UTF-8 positions. But JavaScript, as you may or may not know, actually uses UTF-16. So as soon as you use any special characters, maybe in a comment, an emoji, then positions are completely off, and Rollup heavily relies on positions for its rendering. So, question, can we still use SWC and maybe also fix the conversion time? So we tried something bold. So we did like this. So we still use the parser from Rust, but in Rust, we are now converting the syntax tree to a custom binary format. So each node is encoded as in a binary buffer, in a huge buffer. So while we're doing this, we're also fixing the positions, and we're also making it easy to convert the binary one-to-one back to a fully ES3 compatible syntax tree. And what is the advantage of having a buffer? Buffers can be passed between native code and JavaScript code without copying. Basically, we can use the same memory and directly work on the same memory in JavaScript. So this obviously took a lot of time, but it is done, and we can try out and do some profiling. And what we see now, it takes 108 milliseconds. So we're nearly twice as fast, even though we have the additional step of conversion and converting back. So let's have another look. Where do we spend our time? We know that the parsing took 51 milliseconds. The conversion to binary is actually pretty fast, even though it fixes positions and converts the nodes. It takes 8 milliseconds. This is really good news, because this is the step we're gonna need to keep for the future. The other expensive part is converting it to JavaScript objects, but that is okay. because the plan is in the future to basically move more and more of the subsequent steps into Rust, so that we will not be keeping the last step. So we are already faster now, even though we just replaced Acorn with a drop-in replacement, but we can now grow this and we can expect more and more performance gains as we do that. And there is more. So we have an array buffer now we are creating from the syntax tree. And array buffers can not only be passed freely from native code to JavaScript, we can also pass them freely between web workers without copying. So now we can start parallelizing everything we have as native code. So first we can parallelize the parsing, but if we move more code into native code, we can parallelize more. This will not be part of Rollup 4 release because I'm very interested in getting the release out as quickly as possible to gather feedback and experience, but this will be an improvement that we add very early on. Also, the array buffer is much smaller than the JSON representation, about 1/4 of the size, which means we have very efficient caching. And of course, the deserialization is faster, as you already saw. So this is something where also Rollup's watch mode will profit from. So, and this is the start, as I said. Next steps are we can avoid the JSON deserialization. We could start moving some of the analysis to Rust. So currently, scope analysis, as you saw, is quite expensive. So we can do this in Rust and add it to the array buffer, so that basically the parsed syntax tree also contains information what variables reside in which scopes. We can also offer something to make plugins faster. So we could use a fast syntax tree traversal API, which directly works on the array buffer. And I expect this can be made quite fast, even if it only works in JavaScript. But stay tuned for more. This will take a few months until we get there. Then, as you may know, SWC actually supports directly TypeScript and JSX. This is not enabled right now, because we also need corresponding data structures in Rollup and converters which know what to do with a TypeScript or JSX node. But it's possible to, for instance, have a preserved JSX mode where you're basically keeping the JSX in the output. That's interesting for libraries. Or a convert JSX mode which converts the JSX to pure JavaScript. Similar options are possible for TypeScript. So let's see where we go here, or if we implement this. And last, of course, we want to move the tree shaking to Rust, but let's see how long this takes. But now we have the option, without any breaking chains, to make Rollup faster and faster. And this is a great thing. So what does it cost us? So the additional code we have at the moment is about 2.5 megabytes, which is much smaller than SWC actually is. And the reason is that we are only including the parser from SWC and nothing else. And we are compiling our own native artifacts. We're not reusing the official artifacts. We're already creating binaries for the most common platforms and architectures and have a WebAssembly build if your platform may not be supported. Similar, the browser build now also needs a WebAssembly file, which makes it a little more difficult to use. Well, that's the price, basically. But then again, the browser build still uses the same code base, which is also important for the REPL. And you can try it out now. So install Rollup at beta. This will definitely work. Maybe we have a stable release by ViteConf. Keeping my fingers crossed, but I don't want to make too many promises here. I'll tell you when this is broadcast. So there's one question I want to talk about. What about Rolldown? So Rolldown by itself is a fast JavaScript TypeScript bundler in Rust with Rollup compatible API. So basically it is a rewrite of Rollup. And what do I think about this? The thing is, there is a dilemma for rewrites, where I want to say, unless you have several people working on it full time, the rewrite will just drain resources from Rollup without ever replacing it. Because Rollup wasn't written in a day. Rollup was written 2015, and there have been thousands and thousands hours of refinement and new features that have been added to Rollup. And you cannot just rewrite this in a few months, especially if you're starting from scratch and not looking at the original sources. So what Rolldown is doing, which is a good thing, they're using the tests of Rollup, at least a part of the test suite, not all of them, and working against that. And the thing is, I'm not opposed to this project. I really want to say that. If I see a chance that it will be covering nearly 100% of Rollup with a similar output quality, which means similar code analysis features and tree shaking in reasonable time, I would actually switch to that project and make it the next major Rollup version. Because I think it's a good thing. I just think it's difficult to do this in a timely manner. So this also goes to anyone who wants to finance this project. If you can put a few $100,000 in that direction, let's talk. Okay, so that being said, for the end of my talk, just want to dream a little. So if I wanted to do, or if I could do whatever I want for Rollup, what would I like to do? So just 3 features I quickly want to talk about. The first thing would be statement level code splitting. Just imagine, so at the moment, modules are the smallest code splitting units you have in Rollup. So if your source code is in a single file, unfortunately Rollup can only create a single chunk. And this is sad. I mean, like, if you have 10 function declarations, why do those need to be in the same file? Basically, as they don't have side effects, you could do it a different way. You could say, okay, I'm looking at the top level statements in my file. So, and see what are the dependencies of these statements. So if the statement has a side effect, maybe the side effect needs to come after the previous side effect in one of the lines above. And if it depends on a variable, of course, it needs to come after the variable declaration and all mutations of that variable. So then you can create a dependency tree not between modules, but between top-level statements. And you could feed that into the code splitting algorithm to get a much better chunk graph. So that's just an idea, and it will be a lot of work because it will basically fundamentally change how we do that, and also could be costly performance-wise. Maybe if this comes, it will need to wait until the Rust conversion is gotten a bit bigger. The next would be object property tree shaking. This would be easier to do because we have a lot of analysis. We already know when we can no longer trust a property in an object. And using this analysis, we could also remove unused object properties, which would mean you have a large object like configuration objects, and then you can basically reduce the size of object. I think the impact will not be as big as that of the previous feature, and also not sure about the performance impact, but also something I wanted to do for a long time. But the last one is probably the most important to you, which would be, let's put it like this. People said that Webpack's code splitting is better than Rollups, and that depends on the constraints you take into account. So Rollup's constraint is that you never duplicate code and never ship any dead code, which comes from Rollup originally being a bundler for libraries where I really do not want to duplicate code. But if you're bundling for the web, you have different constraints. It's okay maybe to put a module into different chunks if you reduce the number of chunks. So imagine you're loading an entry point and all the dependencies for that entry point are together in the same chunk. So you only load a single file, which will be great for search engine optimization, and all dynamic imports then pick small bits and pieces. But to do that, you have to put the same files into different chunks, and then there needs to be some logic that decides, okay, has this module already been loaded? Then the next loading of that module is just dead code. So that's something to take into account, and probably the thing I would work on first. But that's all I wanted to talk about. Thank you very much for listening. I'm very interested in your feedback, especially if you try out the beta build of Rollup, or maybe the final build if Rollup 4 is out. See you on the conference. Bye. And just mentioning, and my head is in the wrong position. So the examples are also found on GitHub if you want to play around with this.